Alright, so enough history of atoms. Let's start looking at a more modern view of atoms. And we'll start with the electromagnetic spectrum, which I'm hoping this is somewhat familiar to you. It kind of ranks different forms of energy, different forms of light waves and gamma and radio waves, all that good stuff, by increasing energy and also increasing, decreasing wavelength, which we'll look at in a minute. The gamma, X-rays, ultraviolet, these are all your high energy waves. So write that in. Over here, this is my high energy. On the opposite end of the spectrum, your radio waves and microwaves, these are all low energy. And then we've got the visible light spectrum kind of in the middle, which obviously we're all familiar with the colors of the rainbow. Although, have you heard like indigo might get booted from the rainbow? That's like super controversial right now. With the colors of the spectrum then, the violets are high energy. And the reds and oranges, these are your low energy. Low energy colors of light. So if you look at that spectrum, ultraviolet means above the color violet. So ultraviolet rays are just a little bit higher in energy than violet visible light. Infrared means below red. So they're a little bit less energy than red visible light. Okay, let's break down these waves a little bit more. We talked about the energy level. You'll notice this wavelength marked across the bottom. So you might remember from a previous science class that the wavelength is the distance between two waves. You can either go trough to trough or peak to peak. So like this might be my wavelength. I'll go somewhere in there. So if this is the red light, this is low energy. I'll put that in here too. Low energy. It has a longer wavelength. The longer the wavelength, the less waves you have per time, which means low frequency. Frequency is just the number of waves per time. If you look at violet, this should be a higher energy color of light. So put that in, high energy. And now let's say I go trough to trough. I pick out one wavelength. You can see that this wavelength is shorter. A shorter wavelength means there are more waves in that given time period. That's a higher frequency, higher energy wave. These units that are used are micrometers. This is kind of a goofy metric symbol for micro. So we're measuring these in tiny, tiny fractions of a meter. Okay, so now if we look back to our previous models of the atom and everything that anybody's ever told you about atoms, we kind of figure that these electrons are little particles, right? They're these little particles that fly around the nucleus in some kind of energy level. That's what my teacher told me, right? Let's mark that down. We first think that electrons were seen as little particles. Okay, and I'm not going to argue with that. I think there's some credibility to that. When atoms have their electrons in the lowest energy level, we say that the atom is in its ground state. Ground state. So when atoms, and we can even say like when the electrons in the atom are at their lowest energy level. We say they're in the ground state. Now we've kind of mentioned these energy levels where, there's some energy levels that are real close to the nucleus. Those are low energy. And then as you move further from the nucleus, those are higher energy levels. Now here's where it's going to be a little different. Here's the modern twist. We usually think that an electron is in a particular energy level and it's stuck there for life. This electron is in energy level 2, and you're going to fly around the nucleus in energy level 2 forever and ever. But now we have evidence that might not support that. When electrons absorb a very specific amount of energy, they can jump up to higher energy levels. But in order to be at a higher energy level, you obviously have to gain that amount of energy. If that happens, now we say that the electrons are excited. Or sometimes you might hear like, the electron is in an excited state. That just means that it has jumped up to a higher energy level than it would normally be found. If home base, the ground state, is energy level 2, and this electron gains energy, maybe he can jump to level 3 or 4, maybe even 5. Oh, okay, so here's like the modern twist. Okay, so let's visualize all this. Here's my atom. Here's my energy levels. And again, we said that energy levels close to the nucleus, these guys in here, these are low energy. As you go further from the nucleus, these are going to be higher energy levels. Okay, so let's say I have this lonely little electron. Let's kind of plunk him right here. I'm going to actually put him in the first energy level. Let's say he's starting in the first energy level. And I'm going to say level 1 is ground state. He's in level 1, that's ground state. We'll even write that in. This is ground state. Ground state. Now, ground state doesn't have to be level 1. It's just the home base, where that electron is normally found. Ground state could be energy level 5. If that electron is normally in level 5, then it's ground state. We'll say this guy's ground state is level 1. Now, what if I do something to add energy to this electron? We're going to do it. There's a couple of ways you could add energy. One would be maybe an electric current. We'll do that in class. In a way, I guess we're kind of electrocuting the electrons. That's kind of exciting. Or in the lab, we can add heat energy, and that should excite the electron, which means it's just jumping to a higher energy level. Okay, so let's say we just add a small amount of energy, and this electron jumps from level 1 to level 2. That electron is now excited. It's in a higher energy level than it would normally be found. Now here's the bummer. The excited state is not stable. The excited state is very unstable. So it may sound all cool to be in the excited state, but the electrons would actually be back in their ground state. In order to be more stable, they'd like to fall back down to their ground state. Want to go back home. So because that excited state is not stable, the electrons will fall back down to the ground state. But in order to do that, they need to release a very specific amount of energy. Each energy level contains a specific amount of energy. So in order to jump from level 1 to level 2, you have to gain that perfect amount of energy to be allowed in level 2. And there's no halvesies, so you can't be like hanging out between levels 1 and 2. If you don't have enough energy for level 2, you're going to stay in the ground state level 1. In order to go from level 2 back down to the ground state, we need to release that extra energy. And so when he falls back down, we release that extra energy, and often it's in the form of light. In this case, if we only gained a small amount of energy, we only jumped from level 1 to level 2, then we're just going to release that small amount of energy. If the energy is released in the form of visible light, we should be able to see specific colors. It's very cool. We're going to do this in class and the lab. So a low energy color might be like red. So here's what's so wild. We cannot see electrons. Nobody can see electrons. But by looking at the color of light released, we can kind of predict what's happening to the electrons. If you see red light being released, you know that the electrons are just making small jumps. They're gaining small amounts of energy, and then they're releasing small amounts of energy. That translates into lower energy colors, like maybe the reds or the oranges. However, let's say I have another electron. Let's put him in ground state. We'll make his ground state level 1 again. But again, as I said earlier, ground state doesn't have to be level 1. It's just their normal home base. So here's another electron in level 1. Let's say this time we really crank it up and we electrocute the snot out of this thing. Or we go in the lab and we just scorch it. This time he makes a bigger jump. Let's say he goes from level 1 to 2, 3, 4. Jeez! Okay, so if we add more energy, the electron can jump more energy levels. But again, being in a higher energy level is not stable. The excited state is not stable, so the electron wants to go back home. He wants to go back down to his normal ground state. But in order to go back to level 1, he's going to need to release that extra energy. If that extra energy is released in the form of light, now we're going to see a higher energy color because we absorbed more energy to go up 4 levels. So in order to fall back down, we need to release that energy. And now this time it might be like blue light. Or maybe it's violet. This time maybe I'll see a higher energy color. So again, in a lab we'll look at these colors of light released when they excite electrons. We're going to add heat in the lab. And one of the lab questions might say, like, even though you can't see electrons, in which element did you see electrons making the biggest jumps? Well, what I'm going to see visually is the color of light released when the electron falls from the excited state back down to the ground state. If I see higher energy colors, like the blues and the violets, the electron was gaining more energy and releasing more energy. If I see low energy colors like the reds and the oranges, then I can predict that the electron was just jumping small levels, maybe 1 energy level, maybe 2 energy levels. We gained a small amount of energy and we're releasing a small amount of energy. Every element will produce a very specific pattern of colors when you excite their electrons and you run that light released through a prism. The specific colors released are called the bright line emission spectrum. So it's specific bands of color that you'll see when you run the light through a prism, and it's unique to each particular element. So it's in a way a good lab technique for identifying an unknown element, which is exactly what we're going to use it for. So here's kind of the deal. If you run white light through a prism, it's going to separate and give you all the colors of the visible light spectrum, all the colors of the rainbow. Here's exactly what we're going to do. We're going to take these tubes of gas. So this tube is hydrogen gas. We're going to electrocute it. We're going to hook it up to a power supply. It's going to glow. Hydrogen is going to give off kind of this like purple glow. It's obviously, like you can see, it's purple here. You can't see in your study guide. It's just printed black and white. But you're going to see like this really purple light. Beautiful color, actually. Then we're going to run that light through a prism. And you'll see these specific bands of color. This pattern of colored bands is called the bright line emission spectrum for hydrogen. You should see a really strong red band, and then there's kind of like a teal, and then kind of like a blue and a purple. No other element would produce the same pattern of colored bands. So it's exactly what we're going to use it for in the lab. Experimentally, we're going to look at unknown samples and compare them to known elements. And we'll try to figure out what elements are in the unknown by looking at their bright line emission spectrum. It's beautiful, isn't it? We can also then kind of predict what's happening to the electrons. If we see more reds and oranges, they're making small jumps. If we see more high energy colors like the purples and the blues, the electrons are gaining more energy and then releasing more energy. So to kind of sum this up, there's something called now wave-particle duality. It's kind of a modern theory. And it really says that we think electrons have properties of both particles and waves. I'm okay thinking that an electron is a little particle. Whenever you see pictures, electrons are drawn as little particles flying around the nucleus, and I'm not going to disagree with that. I do think they're particles. They have a position. Or a location. Like we can say this electron is at energy level 3. Well, that makes me think it's a little particle. I can locate this little particle at energy level 3. And they do have mass. The mass of an electron is really tiny, but it does have mass, which makes me think it's a little particle. However, now we've learned that moving electrons, here's my little symbol for electron, E minus, because electrons are negative. Moving electrons can emit light waves. Which leads us to the wave-particle duality, where we believe electrons can act as particles or waves. And again, this whole concept is really awesome, and it's something that we will look at in much more detail in class and in the lab.